Okay, let's talk a bit more detail about a transfer function. So I rewrite again the generic form of a transfer function. We discussed this in the previous few slides. So in the case of a system, a dynamic system, where the dynamic system involves not only the first derivative of the output, but it also involves the higher derivatives of the output and any derivatives of the input. You have seen this equation before. So this is we have a system with this generic transfer function. It looks complex, but what we can see here, if you look at this transfer function, the numerator appears in the m polynomial of s, and the numerator appears with a n polynomial of s. This polynomial function of s, you can always factorize it as if, let's say, for example, I have a second order polynomial of s squared plus 4s plus 3. You will always be able to factorize it into s plus 3 and s plus 1, into a combination of two first order polynomial, right? Linear function, s plus 3 plus s plus 1. Any high order polynomial of a function of s in this case, you can always be able to factorize it also. So same thing to this transfer function, you can always be able to factorize both sides, the numerator as well as the denominator. Let's take a look on the numerator. Since we have m polynomial of s in the numerator, if you factorize it, you will have m factors in this case, right? And then for the denominator, we have n order of polynomial. If you factorize it again, you will have n factors. So after I factorize it, both of them, I factorize the numerator and denominator, my transfer function of this generic system appears like this. So for simplicity, I will just call the numerator with ns and the denominator as ds, like that. Okay. In this course, there will be a lot of new terms. So I will introduce you to the first new terms that you will use it frequently in this course. The new term is poles. What is pole? Poles are values of s that will make your transfer function gs equal to infinite. So you just have to find the value of s that will make your gs equal to infinite. What are those values? Those values are, the first one is negative p1. Why? If I replace all of the s's with negative p1, I will end up into 0 for this one. Negative p1 plus p1 is 0. So this will become 0. All of the other factors are non-zero. So the denominator now is 0 because I multiplied with the 0. I will have 0 in the denominator. And any value, if you divide it by 0, will become infinite, right? So your gs will become infinite if you take s equal to minus p1. So in this case, definitely minus p1 is one of the poles. But negative p1 is not the only pole in your transfer function gs. Negative p2 is also another pole. Because if you substitute negative p2 to the s's here, this term will become 0. If this term is 0, the denominator will become 0. Any value that you divide by 0 will be infinite. So your gs is infinite. From there, it's clearly that negative p2 is also a pole of this gs. Obviously, negative pn is also another pole of this gs. Okay? So, how to find the poles of this gs? Basically, how to find the poles of this gs? You just have to find the roots of the denominator. Find the roots of this equation. The roots of this equation will tell you the poles of the GS. In addition to poles, I want to introduce you another new term, which is zeros. So this is a term zeros. It's not a value of 0, but this is another term. We call it zeros. What does zeros mean? Zeros are the values of S that will make your GS equal 0. So you see the difference between zeros and poles. Poles are the value of S that makes your GS equal to infinite. But for zeros, zeros are the value of S that will make your GS equal to 0. What are those? Obviously, when your S is equal to negative Z1, the first term in the numerator will be 0. 0, if you divide it with any value, will become 0. So negative Z1 is one of the zeros. Negative Z2 is also one of the zeros, because if you substitute negative Z2 to the S, you will end up into 0 in the numerator. 0, if you divide it with anything, it always 0. So negative Z2 is also the one of the zeros of your transfer function. Negative Zm is also one of the zeros, of course, here, right? So at this point, then I have already introduced you to poles and zeros. But that's not all. There is one more thing. There is also another term that we call as infinite zeros. Infinite zeros is different than zeros. So what is infinite zeros? You will have infinite zeros if the order of the denominator is higher than the order of the numerator. Okay. If you have this case, if you have a case when the order of denominator is higher than the order of numerator, then in addition to poles and zeros that you have already identified, you will also have infinite zeros. In particular, you will have n minus m number of infinite zeros. So as a summary, then, if you have a generic system with the generic transfer function as we discussed in the first equation of this slide, as a summary, then you will have poles with n number. So you have n number of poles. You will have m number of zeros, okay, the ordinary zero. But in addition to n poles and m zeros that you have here, you will also have n minus m infinite zeros. What does infinite zeros mean? Infinite zeros mean when you substitute infinite value to the S in your GS will become 0. Okay, now let's take a few examples on how to identify poles and zeros of a system. Let's take a case of a GS where GS, the transfer function, is represented by this equation, right? So if you have this, the numerator of this transfer function is a second order polynomial. Why? Because you have two factors of numerator there, s plus z1 and s plus z2. The denominator, you will have 6th order of polynomial, because you have s square, so you have 2 order there. S plus p1 is 1 order, and then s plus p2 you have 3rd order. So 2 plus 1 plus 3, you have 6th order in the denominator. So from there, you can identify the poles easily. The poles are the value of s that will make your GS equal to infinite, right? We discussed this. So what are these poles? The first one, of course, is minus p1. Why? Because if you substitute minus p1 to all of the s's, for this term will become 0. So your denominator will become 0. any value when you divide it by 0 is becoming infinite. So negative P1 is one of the poles. 0 is also poles. I mean, 0 value is not zeros, but 0 values. 0 value is also a poles of the system. Why? Because if you substitute 0 to all of the s's, the first term in your denominator will become 0. S square, s is 0, so the first term will become 0. The denominator will become 0. Any value you divide by 0 will become infinite. But of course, in here, you have two poles where s is equal to 0. So you have one pole at minus P1, you have two poles at 0 value. In addition to that, we also have 3 poles at negative P2. So when s is equal to negative P2, this term will become 0, and then your GS will become infinite. But we have 3 poles at negative P2 because this term has an order of 3. Okay? So in this system, we have 1 pole at negative P1, twin poles at 0, and 3 poles at negative P2. What about the zeros? Zeros are the value that will make your GS equal to 0, equal to null. So obviously from this equation, the zeros of your transfer function are minus z1 and minus z2. If s is equal to minus z1, this term will become 0. So your GS will become 0. If s is equal to minus z2, then this term will become 0, right? And your GS in turns will also be equal to 0. So you have 2 zeros in your transfer function here. You have 6 poles, the one that we discussed in the previous slide. The order of the denominator is more than the order of the numerator. You have 6 for the denominator. For the n, you have 6. You have 2 for the order of the numerator. So your m is 2. Because n is greater than m, in addition to all of these poles and 0, you will also have 4 0s at infinite location. So in this case, then you have, again, 6 poles. You have 2 ordinary zeros, or we can call it as finite zeros. And then the last part, you have 4 infinite zeros, 4 zeros at infinite location. Let's take another example again here. I have a system where the transfer function is GS. GS is equal to this equation. You can see it here. The numerator has an order of 2, polynomial order of 2. The denominator has polynomial order of 4. Again, we are going to identify poles and zeros of the system. So how to do that? I need to factorize it first. I need to factorize both numerator and denominator. If I factorize it, it's becoming like this. So the numerator, of course, you can factorize it easily. It's a second order polynomial. It's a quadratic equation. You can factorize it easily using ABC formula. We are very familiar with this formula. The denominator is a bit complex to factorize it. You cannot factorize it easily. You can factorize it, but with the help of a good calculator or computer, you can factorize it easily. Don't worry, I will not ask you to factorize it, but in this example, I will factorize it for you with the help of computer. Of course, I did it. So I have factorized these two terms, the numerator and the denominator. It's becoming this one. Okay. So from here, immediately you can identify the poles and the zeros of the system. The poles are the value of s's that will make your system infinite. So from here, you can immediately see 0 is a pole. If s is 0, this will become 0. The denominator will become 0, and your GS will become infinite. Negative 4 is also a pole, because if s is equal to negative 4, this will become 0. The denominator will become 0. Your GS will become infinite. You have 2 poles at negative 1. because if s is equal to -1, this will become 0. But I have two poles at -1 because this appears two times, this appears twice because of the squared term in the s plus 1 term there. So I have one pole at 0, I have one pole at -4, I have two identical poles at -1. In total, I have 4 poles, right? Because of this, the denominator has a highest polynomial order of 4. What about zeros? Zeros, of course, you can see it immediately from the numerator. So the zeros are -2 and -3, right? Again, the order of denominator is more than the order of the numerator. We have 4 order on the denominator, we have 2 order on the numerator. So in addition to all of the zeros and the poles that we discussed, you will have 4 minus 2. You will have 2 infinite zeros in addition to the poles and 0 that we have. Let's take one more example, the last one. So I have again another system with a transfer function. As you can see in this slide, we are going to identify the poles and the zeros again. So how many poles, how many zeros, and how many poles of the system, and what are those? Let's find the zeros first of this GS. So you can find it immediately from the numerator, right? The value of S that will cause your numerator equal to 0. And those are, you can identify it easily, -2 and -10. What about the poles? We have single poles at 0, -1, and -5. 0 is coming from here, -1 from this part, -5 from this part. And then in addition to that, we have a double pole. We have 2 identical poles at -15. Okay. Of course, in addition to that, you will have infinite 0 because the order of the denominator is higher than the order of the numerator. So again, to illustrate what does infinite 0 means, infinite 0 basically, by definition, zeros mean the value of S that will cause your GS equal to 0. Same thing, by the same analogy then, infinite 0 is the value of S when S is equal to infinite. That will cause your GS equal to 0. So when you replace all of the S's in your GS with infinite value, the GS will become 0. So exactly this is what happened if I substitute infinite value to all of the S's. I will have limit S to infinite 2 of GS. GS is equal to this equation, okay? But now if S is infinite, S plus 2 and S is the same, isn't it? So imagine you have a large number, 1 billion, 1 billion, and 1 billion 2, more or less the same. I don't really mind with the 2 there. So the S plus 2 term, if S is very large, I can approximate it as S. S plus 2 is equal to S if S is very large. As well as S plus 10. 1 billion and 1 billion 10 is more or less the same. So S plus 10, I can approximate it also as 1S, single S, like that. Same thing to all of the terms in the denominator. S is S, S plus 1 is also S, S plus 5 is also S, S plus 15 is also S, but I have S squared there. So I have K S squared divided by S power of 5. This will become K over S cubed, but now S is infinite. Because S is infinite, so K divided by infinite value is 0. So this shows you when your S is equal to infinite, your GS will become 0. So in this case then, infinite value is also a zero to your GS.